Hello, and welcome to Unnatural Numbers, the YouTube chat show where we ask the question, what happened if we take the Graham Norton show but replace all the celebrities and production value with mathematicians and the number 5? Today, on episode 5, we're going to be talking all about our favourite facts for the number 5. And joining me today, I have two fabulous guests. First of all, we have Hope Duncan, who is an emerging debutante on the YouTube maths communication space. Welcome, Hope.
Thanks for having me back.
Thank you. You might remember Hope from episode 3, and she's back here to delight us once again. Also joining us is Jocelyn, who is my boss for this week as the founder and CEO of a new STEM startup company, Poindexter Labs. And I'm sure she'll tell you more about that at the end. Welcome, Jocelyn.
Thank you. Excited to be here and learn.
And up first is my fact. So my fact this week is all about the Aliquot function. Now, you might have heard of the Aliquot function before. So the Aliquot function works a little bit like this. We are going to take a value, k, and find the sum of all of the numbers that are proper factors of k. So I'm going to call this the sum of f, the proper factors of k. Add them all together, that is the Aliquot sum. It's not a particularly difficult concept, but it has some very intriguing results. So let's think about what we mean, first of all, when we say the sum of all of the proper factors. So for this, I might start with the number 4 and consider what is the Aliquot sum of the number 4. So the factors of 4 could be 1, 2, and 4 itself, because those are all of the numbers that will divide the number 4 to get an integer result. But we're not going to include the number 4 itself. We're going to say that one is improper. So the proper factors of 4 are 1 and 2. And if I add 1 and 2 together, I get the number 3. That was quite easy. What about if I take the Aliquot function of the number 5, today's number of the episode? Well, the factors of 5 are, well, it's a prime number, isn't it? So the only proper factor really is just the number 1. Therefore, the Aliquot function for 5 is 1. And in fact, the Aliquot function for all prime numbers is only ever going to be 1. What you might have noticed just then is that we can have two numbers that have the same Aliquot function results. That's quite interesting. Okay, so what about if I ask one of you guys to try this one live on the spot without any preparation? Could you tell me the Aliquot value of 6?
6.
Yep, that's right. Can you tell me the Aliquot function for the value 6?
Is 6.
Yeah, that's the question. Oh, spoiler alert. We'll leave that one for next week, shall we? Because I'm sure someone is going to want to talk about how the Aliquot function for 6 is in fact 6. That's all right. We'll leave that as a spoiler for next episode. Instead, I want to change the game a little bit here, because actually calculating an Aliquot function isn't too difficult. But what about if I started with the Aliquot function of x, where x is an unknown, and I said I want this to be equal to 7? Now, that's a little bit more interesting. Can we find a number whose Aliquot sum is 7 itself? Now, to do this, we might want to start thinking about some of the properties that all of these Aliquot numbers share. So 1 is definitely a proper factor of every single number. Therefore, whatever this number is has to have 1 as one of the proper factors. But then, if we're taking a sum of all of the proper factors, it has to be 1 plus something, which means this something part has to add up to 7 take away 1, 6. Okay, well, there's still a lot of room here, isn't there? So maybe we should just say the number 6. Why not just 1 plus 6? Well, that's a problem though, isn't it? Because if there is a number that has 6 as a proper factor, then it must also have 2 and 3 as a proper factor. So that's not going to work. So how about we pick something else then that's not 6? We'll go for 2 numbers. Well, what about if I have 1 plus 5 and think about what I might have to add to that? Oh, no, that's not so good, because 1 plus 5 is 6. You need to add 1, and I can't be adding 1. I've already counted 1. So it definitely can't be 5. Well, what about if I try something else? Maybe if I try 1 plus 3 is 4, and so then I'll need another, I need another 3, and I've repeated the 3. It can't be done. Okay, so the last thing to try then is, what about 1 plus 2? And then the last one will be 4. And that's absolutely fine, because if 4 is a factor, so is 2. 1's always a factor. I'm golden. So what was this number that's a multiple of 1 and 2 and 4? Turns out to be 8. So the Aliquot sum of 8 is indeed 7. Absolutely fantastic. So can I give you guys a one to try? So have a go at this one yourselves. I want you to find the Alcott number of x such that the sum is equal to 10.
Well, I know for 2 to the p minus 1, you can always get 1 less because there are a number of factors and that's how the 2's all combine. So the a of 8, that's the a of 8 being 7. So a of 16 is 15.
Oh, okay. So you're
And
going to
a
say
of
that the Alcott
32,
number,
yeah, is 31.
so you're saying that the Alcott number of 2 to the power of p take away 1.
No,
I think what you
2
might
to
mean
the
is
power 2 to the power of p plus 1, I think. Or no, 2 to the power of p minus 1 in so
is
take
the Alcott sum of 2 to the power of p.
yeah.
I think this is valid because this
I think
has
that
all
one
of the
works.
numbers 2 to the power of k, such
Yeah.
that k is strictly less than p.
Yeah.
Which when summed together with the number 1 as well, will give you, which will give you 2 to the power of p minus 1.
Yeah.
Yeah, I think that works. That's one of the rows of Pascal's triangle, isn't it? Okay, great. But what about trying to get one that has the number 10? Because 10 doesn't fit that format.
That's
So
what I'm thinking.
14, I think, works for that, right?
14, should we test 14? So a of 14. So this has the proper factors of 1, 2, and 7. And indeed, they all add up to 10. 10 points to Hope. Well done. So that's quite fun. And we could play around with this game and see if we can get lots and lots of different answers. And indeed, we can get many numbers. Pretty much all of them will end up with one of these Alcott sums. But there are a few that don't. And I'm more interested in the ones that are not the results of the Alcott sum. So for instance, can you find a value k such the Alcott sum is equal to 2? Now, here we might have run into the law of small numbers. 2 is just so tiny that there's not very many ways to partition the number 2. It has to have the number 1 as one of them, and then the other one has to be, 1. Well, that can't be done. This is a fairly easy example then of a number that cannot be written as an Alcott sum. And because it can't be touched by the hand of Alcott, we call it an untouchable number. So if we were to look for another untouchable number, I'm thinking about today's episode, could I ask you to come up with any kind of guess you like for what might be an untouchable number?
5?
It turns out that 5 is the first odd number that is not touchable by the Alcott sum. A of k is never going to be equal to 5. That's my fact today. Being an untouchable number of its own isn't that unusual. There are, in fact, an infinite number of untouchable numbers. The next one after 5 is 52. But 5 is unique for being the first odd number. Now, here is my real fact for today. 5 is also the last odd number that is untouchable. Asterisk. You might have noticed a small asterisk there, so let me evaluate that. This is the last odd numbered untouchable number that we know of. So this is actually an open area of research. Nobody knows whether there is going to exist another odd number that is not expressible as an Alcott sum. We just don't know. We've tested this up to about 10 to the power of 18 numbers, and so far found they are all evens except for the number 5. Now, do you notice anything interesting about that value 10 to the power of 18? It's been a number that we've seen before on this show as something to test up to. It does in fact link to Goldbach's conjecture. If we have proven Goldbach's conjecture, so this is that every number is expressible as the sum of 2 primes, then that also proves that 5 is going to be the only odd number that is untouchable. And that's what we've tested up to 10 to the power of 18. How are these two linked, I hear you ask? Well, for that, I'm going to let you go off and do a maths degree to find out, because it is a little bit beyond the scope of this chat show. But that's why I think the number 5 is cool.
I was gonna say Goldbach's conjecture. I was actually gonna, because it's linked to Martin Gardner's impossible puzzle.
Tell us more. What's that?
something like there's two people, person A and person B, and one knows the product and one knows the sum, and one says, I don't know my numbers, and the other one says, neither do I, and then the other one says, now I do, and then the other one says, now I do. And the order that they say it in matters, but it's all to do with how many different ways there are of partitioning it with the factors. And then, you know, like you could rule out that it can't be prime, because if it could be prime, then you basically have to iterate back. Like I said, I'm not smart enough anymore, but I did it. It was like 3 days and 20 pieces of paper, and then realizing and making injections. And then when I was telling someone about it, somebody said, oh yeah, you can use Goldbach's conjecture for that.
Sometimes it is just easier to prove Goldbach's conjecture first and then get on with whatever you were doing that day.
Yeah, well, nobody's proved it yet, so
One thing I find really interesting about the world of these open problems in mathematics is how so many of them are reliant on other ones in seemingly unconnected ways. The Goldbach conjecture has come up quite a few times already, and there's several other theorems that are automatically proven if we've proven that. One challenge I'm going to give to the viewer of this is to come up with some kind of roadmap that shows how everything is built upon everything else, so that as mathematicians globally, we can decide what's the most important thing to focus on that has the biggest effect.
Well, this is because of the one, isn't it? Because it's like Goldbach's conjecture, but then you've got the one that's forced in there.
And I'm sure it also loosely relates to the Navier-Stokes equations, because everything links to everything else. So if we just prove the big ones, we'll be fine. And next up for our facts on number 5, we have Jocelyn. Jocelyn, what's your fact this week?
Hello. So my fact might not seem like it's about the number 5 initially, but I promise we will get there. Most of you probably know the cube root trick, which I call it Matt Parker's cube root trick, but actually he didn't invent it. But for anyone who doesn't know what it is, if you take a 2-digit number and cube it and tell me what you get, I can, like magic, tell you what you must have typed into your calculator. I'm guessing both of you have a, you know, FX83 GT Plus handy or something that you can try this out on me with.
Absolutely, yeah.
Yeah.
So
And
you want a 2-digit number?
Take a 2-digit number and cube it and tell me what you get.
And this isn't a psychology trick?
No.
Okay, so I have got the, let me see if I can write it down for you. I've got the number 300,763.
Okay, so you cubed 67?
Oh my gosh. Yes.
I know.
Is there a mirror? No.
I'm very Hope, did you want to try one?
2,197.
2,197. So that was 13?
Yeah.
Okay. Oh. What if some of your
Brilliant.
viewers have trichostechophobia? What?
Fear of the number 13.
Indeed. Okay, so I think most people know why that works. I can briefly go into it. But so if we can just cube 76 old style as a little example. So start off by doing 76 and then write a 76 underneath it. And then we're going to multiply them together. So 6 times 6. Okay, and then because we need to cube it, we need to multiply it by 76 again. And so we are just going to write the times 76 again, which I know is going to trigger a lot of people because those are not equal to each other, and that's how it goes. But we are also mathematicians and we prize efficiency. So we're going to be efficient. So my question to you is, instead of 76, if this were actually 36, what would stay the same?
The 6?
Yeah, because we would still be doing this 6 times 6, and so that would still be there. And that just drops down to here. And that is here because we put it there. So we would still have a 6 times 6. And so that 6 would still be the same. What if it was 16 instead of 76? What can we say about that number?
It looks like you're making an invariant then. So it's always a 6, isn't it?
Yeah. So any number that you take that ends in a 6, when you cube it, you're going to get something that ends in a 6, right?
Okay.
Now, what if instead of a 6, this was a 5? We'd do a 5 times 5 here. That would put a 5 here. That would carry down to being a 5. Then we'd have to multiply it by a 5 by design. So it would go to a 5.
Yeah.
Yeah. A 4 would be a 4 times 4, which would turn that into a 6. And then we'd do a 6 times 4. And so that would turn it into a 4. 3. So we'd do a 3 times a 3 to give us a 9. And then we'd be doing a 9 times a 3, which gives a 7. Two times 2 would be a 4. And then we'd have to do that 4 times a 2, which would give us an 8. 1 would be a 1 times a 1 times a 1, so that's a 1. 7 would be 7 times 7, which is 49. And then we'd have to do the 9 times the 7 for 63. So we'd get a 3. And for an 8, we would do 8 times 8 to get the 64. And then we'd have to do the 4 times 8 to get the 32. 9, we do 9 times 9 to get 81. And then 1 times 9 to get 9.
So you're telling me that the units column is always predictable when you're doing cubing?
Exactly. Always. So the trick is based around actually just knowing the first 9 cubes. But I'm not going to go into that because other people can look at that and practice it and impress their friends. And if their friends aren't impressed by that, they need different friends. But what I am going to do is talk about a little extension of this because I was having some fun and I thought, well, first of all, I wanted to know why it worked. And that actually centers around the number 5, but that's not what I'm going to talk about. I'm going to talk about something else that happens that I think is kind of cool. So these are the last digits when you cube it. So when we have something to the power of 1, so if we start with an x to the 1, brilliant. And then let's look at the squareds. And I'm just interested in that last digit, okay? So when we're squaring, okay, we get 1, 4, 9, and then that's 16. So let's just, 36, and then we're going to have 49 and 64. Yeah, and would you mind just erasing the tens column so we can just focus on that last digit?
This is like the opposite of rounding.
Yes, exactly.
Like a left truncate.
Okay, so we can see we've got 1, 4, 9, 6, 5, 6, 9, 4, 1, which automatically explains why this trick isn't going to work with square numbers because they're not unique, whereas the cubes, they were unique. So now let's go back to the cubes. Let's look at those. We know those, but we might have forgotten them anyway. But so if we have x cubed, then we get the 1. Let's look at to the power 4.
Oh, this is a lot of mental gymnastics trying to do this.
Well, yeah, but remember, we only care about that last number, that last digit. So the last digit of 1 times 1. I think you can handle that. Come on.
Can, yeah. And I'd like
Flex
to
those
pretend I
maths
already know
muscles.
my
Okay,
powers
2
before.
times 8, the last digit of that is going to be a 6. 3 times 7, the last digit's going to be a 1. 4 times 4, our last digit will be a 6. 5 times 5, our last digit's going to be a 5. 6 times 6, last digit's a 6. 7 times 3, last digit's a 1. 8 times 2, last digit is a 6. 9 times 9, last digit is a 1. So even power, we've got that symmetry again. And now we've really just got 1, 6, 1, 6, 5.
Yeah.
Yeah. Okay. Then let's see what happens for x to the 5, because, you know.
Link back to last episode. These are all palindromes as well.
Yep. The even ones are all palindromes.
So x power. So now I'm just doing the x to the 1 times the x to the 4 mod 10 and writing my answer in mod 10. So
yeah,
1
we
times 1
just
is
care about
1.
the units digit. So we get a 1.
2, 4. It's also 5. 6 times 6 over 6 is 6.
Yeah.
7 times 1 is 7. 8 times 4 is The 48, slow down. And
6, yeah,
it's
48. And the last one?
that is the last one, isn't it?
Yeah, there we go.
Wait, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Get out of town.
Yeah, there we go. So when we raise any number to the power of 5, the units digit is going to be preserved. And there's interesting ways to do that. If you know about modular arithmetic, then you can see what's happening with the modular arithmetic. But the way that you can do it by looking at the number 5, using the number 5, is about thinking about the numbers 1, 2, 3, or 5, because that, if you notice, the 5 is invariant the whole time. So they are the palindromes, the even ones are the palindromes, but that 5 just runs across. It never changes. So when in maths you're confused about something and what's going on, one of the techniques that I like to use is, well, what's staying the same? Because if something is invariant under the change, that might give you a little bit of a clue about the change that you're seeing. So if instead of thinking about 1 as 1, if we think about it as 5 minus 4, like that, and what we can look at is actually doing kind of a binomial type expansion. So if we were to do, for example, 5 minus 4, and it's a little bit easier to almost see on the 5 minus 3, but if we were to look at 5 minus 3 to the 5 and do a binomial expansion of that, and I'm going to clear so that I have enough space for the, sorry, 5, not 2. For the binomial expansion of that, we're going to go one lot of 5
Sorry.
to the 5. So 3 to the 5 is going to be our binomial expansion, like that, right?
Negative.
Negative, thank you. And what we can see is that what we're kind of interested in is how this only affects the units digit. So this one and this one aren't going to affect the units digit because they have a 10 that's already in them, right?
Mm-hmm.
And these two, what we can look at is factoring them. So what do they have in common? So because we only have odd numbers in here, these are only ever going to be odds because they're made up of 5s and 3s. Then when we subtract them, we're only ever going to get an even number.
Okay.
And then we're going to be multiplying that by a 5. So 5 times an even number is always going to be a multiple of 10. So these are never going to affect the units digit.
Okay.
And that's true whether it's 5 minus 3 or 5 minus 1. And if it was 5 minus 4, then your job's already done for you. They're already even because you've already got the 5 and then you've got 4, which is an even number raised to some power. So those are never going to affect the units digit. So the only things that are going to affect the units digits are these two here. And you might notice that that's why it explains the palindromic nature, because whether we are kind of adding them or subtracting them, which is, what's going to happen. So the first 5 numbers, if you look at them as 5 minus 3, that would be 2. Then 5 plus 3 would be 8. If the only thing that we care about is the units digit, these are going to go right regardless of whether there's a minus or a plus in front of them. Because if we add 2 odd numbers, we get an even number. If we subtract 2 odd numbers, we get an even number. So we can see that what we're left with is this 5 to the 5 minus this 3 to the 5 here. And 5 to the 5 is going to end in a 5. And 3 to the 5 is going to end in a 3. And so we have the 2 that we know that 2 to the 5 ends in.
Right. Okay.
And you could work that through for any of them. So it relates to modular arithmetic, but you can do it all just based around the number 5. You can show why the cube root trick works and why when you raise anything to the power 5, the digits unit is going to be preserved.
That's really cool. I like that. Can I write something down on your
It's
working here?
really, but it's so beautifully presented.
Well, I just want to make sure that any high
How
school
could you
teachers that
possibly
are
improve it?
I want to make sure that any high school teachers that are currently watching switch off now and don't listen to Hope's part. But I think what you might be saying is that 5 plus or minus n to the 5
Yeah.
is equal to 5 to the 5 plus or minus n to the 5 brackets in mod 10. Now, this is just like a real trigger warning for me personally. I don't know if it affects you guys much, but I see this kind of nonsense all the time on students' work. But you're saying that in mod 10, that is true.
Yes. Yeah.
That's incredible.
And what I like about it is that, you know, sometimes for a high school teacher, as soon as you see mod 10, that's scary because that's not anywhere in the A-level syllabus or the A-level further math syllabus. But actually, you don't need to know anything about mod 10. Really, all you need to know is that 5 times 2 or 5 times any even is going to be a multiple of 10. And that adding 2 odds gets you an even, and subtracting 2 odds gets you an even.
That's beautiful. I think this might now become my new standard proof to go to when we introduce proof at A-level, because that is, as you say, really achievable, but also very beautiful.
Well, I just discovered it because I did the trick for somebody and impressed them sufficiently, and then they asked, but why does it work? And that's what I went away with, and yeah, came back.
Nice. That's lovely. Thank you so much.
Does that now mean that if I give you a 2-digit number to the power of 5, you can tell me the 2-digit number?
No, I can't. I could tell you the original second digit of it.
Interesting. Okay.
But that's only because you haven't memorized your powers of 5.
Exactly. Yeah, if I memorized my powers of 5, I could do the rest.
I think if you ever meet Matt Parker, you need to memorize this beforehand and do it back to him.
I know Matt Parker pretty well, actually. We're good friends. But yeah.
Well, maybe not anymore after this. That's a slam down if ever there was one.
No, I've said that this is the trick that he popularized and I have exploited on some large integer value of n kind of Tinder dates, I would say. To great success. But no, I definitely got it from him.
Just to clarify, you're saying that this isn't something that you've researched or read from an academic paper. This is just you sitting down and trying to figure out how it works based on your own intuitive. So we could call this then the Darcy proof.
Sure.
Fantastic. Congratulations. That's great. And that brings us on to our third fact of the evening. Hey, that brings us to you. What's your fact tonight?
So my fact is that the first regular polygon that we can't use to tile the plane to make a tessellation is a pentagon. So a regular polygon with 5 sides. So the immediate questions, I'm sure, are what do I mean by tessellation and what do I mean by a regular polygon? So by tessellation, imagine a surface, just a sheet of paper, as big as you like. And what we want to do is using one or more tiles, we want to cover that sheet of paper or that wall, however you want to think about it. So the rules that we have for it to be a tessellation is that we can't have any gaps and we also can't have any overlaps. So like you would if you were tiling your bathroom. So second thing, what do I mean by a regular polygon? So this is a shape that has all of the same angles and the same length sides. So there are, by that definition, technically 2 types of regular polygons that we can talk about. So convex regular polygons or star regular polygons. So to give you an idea of what that looks like, if I was to draw a convex regular pentagon, that would be probably what you're familiar with. So something that looks a little bit like this. So it's not the most accurate drawing, but if we think here, all of those sides should be the same length and the interior angles should be the same. So we can actually also have this as a 5-point star. So we have the same thing going on, right? The interior angle of the star here, these are all the same, and the sides of our star are all the same length. But that doesn't look like a very good tile, right? So for our purposes, we're going to be thinking of these convex polygons. So what I'm claiming is that a regular pentagon is the first shape that we can't use as a nice tiling. So squares are regular, and equilateral triangles, they both work very nicely. So I can show you a couple of examples. So here we have no overlaps and we have no gaps either, but we can't do that with a pentagon. And there's quite a simple proof as to why. And it all has to do with the degrees around a point. So 360, right? So if we look at a particular point on here, so there's going to be 360 degrees around that point. And we have 4 squares around that point. And each of these are going to have, because they're squares, interior angles of 90 degrees. 360 divided by 4 is 90. It's not super surprising, right? But we have a very easy formula to look at for some regular polygon, what its interior angle is. So it's something that people may well have seen before. So for an n-gon, so a shape with n sides that's regular, the formula that we use is 180 times by n minus 2 and divided by n. So can either of you immediately spot the problem that we have if we try and do this with a pentagon?
Yeah.
So the problem is that 108 doesn't go into 360.
Yes, exactly.
Well, without a remainder.
Yeah, exactly. So we can't have a whole number of shapes that are pentagons meeting around a single point. There's always going to be, I think, what's it, between 3 and 4? So I think if we had 3 pentagons, there'd be a gap. And if we had 4 pentagons, they'd have to overlap. So I will admit that I did slightly choose this fact, not because it's particularly shocking if you really think about it, but more as an excuse to talk about shapes tessellating the plane, because I think it's very interesting. The reason that the fact that I gave is a little bit of a cheat is because there are only 3 regular polygons that we can actually use to tile the plane. So we know that equilateral triangles, we know that squares both can be used. Do either of you have a guess as to what the other polygon is?
I think it might be, well, we want something that's going to go into 360. So let's try 6.
I was a little bit confused by this first picture because I thought this was hexagons when I first looked at it.
Well, exactly right. So I do have a separate picture, but you're exactly right. You can, by looking at this first one, see that we can also do the same thing with a hexagon. So if we want our shape to be regular, we can use triangles, we can use squares, and we can use hexagons. But that's it. None of the bigger ones will cleanly go into 360. So we would always have either a gap or an overlap. But while I have a captive audience, there are a bunch more interesting things we can talk about in terms of tessellation. So I thought we would do a bit of that. This is a tiling using a pentagon which is not regular. So if you have a look, all of the shapes are the same pentagon moved around a little bit, but we don't have the same angles and the same length of side. So it's not regular, but we do have this funky pentagon tile that we can cover the plane with. And one of the things that I think is cool is this is very much still an active area of research. So we have known about irregular tilings of the plane using pentagons for quite a while, but the one that I'm showing you in particular was only discovered in 2015, which is surprisingly recent, I think.
So that's only one pentagon we're looking at.
Yeah, so we're kind of flipping it around a little bit, but that is only one pentagon, yes. Okay, let me show you what else I have behind some of my mystery post-it notes. Okay, the other fact that I wanted to tell you, which was the thing that surprised me, is that mathematicians have proved not just that, okay, there exist irregular triangles or quadrilaterals with which we can tile the plane. That's probably not a surprise. But for any three-gon or four-gon, we can tile the plane with them. We need to be careful about how we glue these shapes together, but we can always do it. It's really surprising, I think. And this is just a nice little example of a foregone that if we're careful about how we glue it together, we can tessellate the plane with.
Is it because the interior angles are always going to add up to 360?
Yes.
And so you just need one of each of them, and then you're at the 360.
Yeah, exactly. It's a fact that kind of surprised me when I first heard about it, but when you think about it, if you think carefully about when you are making any sort of triangle or any sort of quadrilateral, if you think about what's going on with the interior angles, if you glue them together correctly, you're always going to be able to find angles to kind of go all the way around your point. Exactly.
I feel like this is one of those really dangerous situations where you can use the word symmetry group.
Yes, you certainly can. Yeah, I mean,
and I think these are not the same symmetry group, are they? Because this one I can see there's no reflection going on, but we do have like a translation, I think, from here to up there. Is that right? But this one seems to have some kind of rotation as well.
The different symmetries are something that is heavily studied within these tessellations, and specifically within translational symmetry. That's something that I'm going to come on to with my last post-it note. So okay, when I first kind of gave you my definition of tessellation, I was maybe being a bit misleading when I said, okay, I want you to imagine a piece of paper or a wall. That's usually what we do, but we do that when we're working specifically in Euclidean space. So traditionally, when we are doing something like geometry, we are studying Euclidean geometry. That's kind of our standard example of 2D or 3D space. But there are plenty of other geometries that we can think of. There is, if you have heard of hyperbolic geometry, the technical definition is a little difficult to give, but the main intuition I would think is rather than thinking of a flat piece of paper, think of a saddle shape. So imagine rather than something flat, something that has the curve of a saddle. We can think about, okay, how do we tile that sort of geometry? So what I have is an example of using a regular pentagon to tile the plane, but not using a Euclidean geometry, using hyperbolic geometry. So this is a really interesting example, I think, of results that might hold in one geometry, not holding in the other. So here, these are pentagons that look kind of different shapes because it's just a kind of 2D Euclidean representation, right? But if you kind of can imagine this bending into a saddle shape, you can see how using these pentagons, imagine kind of straightening out those curves if you kind of projected it onto a saddle shape. Now we can use a pentagon to tile a plane. That's really funky. So it was an open question for quite a while whether we could have an aperiodic monotile. So what I mean by aperiodic was exactly what you were talking about before, Ben, is there are kind of different symmetries going on quite often with these tilings. And one of the things that we can think about is there some sort of translational symmetry going on? So, and we kind of map the points and kind of maybe imagine sort of tracing it on tracing paper and kind of sliding that across somehow. We're doing a translation. So it's very easy to see with something like these squares, we could kind of trace it and just move it along one. And there's translational symmetry there. So what was open for quite a while was, can we have monotile tiling, so just one shape, and that it tells the plane properly, and that it doesn't have some sort of translational symmetry. So this was also posed as, can we find an Einstein tile? So not actually to do with Einstein the physicist, but Einstein in a very German sense for Einstein, one stone. That's kind of where the name comes from. And I actually remember this being solved because what is called the hat tiling that you can see here, this was actually discovered in 2023. So this is very recent. Yeah, I mean, that's kind of, I don't know whether there's much more to say about other than it was very long-standing open problem. I think it's probably fair to say that a lot of people weren't sure that we would ever find an example of an aperiodic monotiling. And yeah, it's very cool to me that we have, this notion of tessellation, which I think is very easy to explain the gist of. It's a problem that you kind of is very visual. You can pose it to someone at the pub, but there is still these, very easy to understand problems that are being solved as recently as 2 years ago. I think it's super cool.
That's beautiful. I really like that. Some follow-up questions for you then. Looking at this, I noticed that not only is it aperiodic in its design, but it's also aperiodic in its degree of vertices. So I can see some vertices of degree 3, and I can see some of degree 4. I don't think we'll see any of degree 6, because I don't think the edges are large enough for that. Do you think it is interesting to ask the question, can you make an aperiodic tiling that has a consistent vertex degree such that you could draw the graph of it and it would be a uniform graph? Or do you think that in order to be aperiodic, you have to have those kind of inconsistent flaws of the graph?
That's exactly what I'm trying to prove quickly. I'm not.
Interestingly, that's actually related to Goldbach's conjecture. And that brings us neatly on to our sequences segment of the show, where we dissect one of the online encyclopedia for integer sequences. And today we have picked A099155. And as a spoiler, this was inspired by a recent XKCD post. See if you can figure out which one we are looking at before we reveal it. So the challenge for you is to construct the longest open path in an n-dimensional hypercube. Let's think about what those words mean, first of all. So we're dealing with paths, so there's definitely some kind of graph theory going on here. We've got n dimensions, so presumably starting with a 0-dimensional object, moving into a 1-dimensional hypercube, 2-dimensional hypercube, 3-dimensional hypercube, and onwards. Hope you're the geometer amongst us. Can you tell me what is a 3-dimensional hypercube?
A cube.
Ah, fantastic. So this is just a cube, but represented in a different number of dimensions. And what do we mean when we say path ape?
So by a path, if I remember my graph theory correctly, so if we kind of imagine we have a bunch of dots, or in this case, we're going to have kind of vertices of a cube or a cube in higher dimensions, a path kind of connects them somehow.
So if I draw you a two-dimensional hypercube square, what's the longest open path I can make here? What makes it open?
So open, I'm going to assume kind of not meeting back to one of the other points. So if we want longest, we're going to be drawing along 3 sides like this.
Oh,
right?
Fantastic. Okay, so let's go back a step. That's the two-dimensional case. If I have a one-dimensional hypercube, I think that's just going to be a line segment. So Jocelyn, what's the longest open path I can make on a one-dimensional hypercube?
It's just a line segment. And
Thank you very much. Yeah.
Yeah.
So it's just a one. Very good. So this has been a little bit trivial so far, but let's see if we can bump it up a notch and go for the three-dimensional case. So for a three-dimensional hypercube, as Hope has already told us, this is just a cube. Let's see if the viewer can do this in their head before you guys do it out loud. How would you construct a path on a cube that doesn't intersect and it's open so it doesn't go back to where it started? Where would you imagine it goes? Maybe if we start from this one.
It's a single path, right? You can't have like 2 trees. They have to be connected to each other. Okay.
So for a path, you've got to not take your pen off the page. It's that kind of job.
So if we get the top 3, maybe.
So we could skirt around the upstairs. Yep.
And then go down.
Yeah.
And then go back.
And then presumably you want to go behind because otherwise we'd intersect. And then we're kind of out of options here, aren't we? So we couldn't go up because then it would touch itself.
No, exactly. No, but we can go behind, right?
We can go behind itself. Yep.
Yeah. So then we go behind.
It's coming. So we're out of choices here. We kind of have
now we're out of choices.
Forwards.
So.
Yeah. So actually, with the n-dimensional hypercube for a longest open path, this is one of those problems that you can't get wrong. In that, so long as you don't intersect with yourself, there's always going to be another option of where you can go in order to create a nice long path. So this isn't a very interesting sequence, and as such, it's not the one I've chosen today. But we're going to add another criterion by saying it's acaudal. Oh, that's another one of those big, scary words. Hope you love your definitions. What do you think acaudal means?
Well, my brain's immediately telling me it's a path without a chord. The key question there being, what's a chord?
Okay, so a chord in this context is any time where you could connect together 2 parts of the path with just one single line segment. So the easiest case here to describe would be in the two-dimensional hypercube in this square. That would be a chord because it connects 2 parts of the graph, 2 parts of the path. In the three-dimensional case, I think the first time we had a chord was this one along here. We went backwards, across, and forwards, and then that was now only one edge away. That's where the chord was. So if we include this extra criterion of acaudal, can we go back and redraw some of these paths and say what is now the longest one that is, in fact, acaudal? Ooh, so exciting stuff.
So this to me just feels like what's the longest path you can draw without letting your opponent win in dots and boxes?
It's a dots and boxes game. Absolutely. Yeah, we should call it the dots and boxes sequence. Although I don't know if any of the literature has made that connection yet. So you can go and invent n-dimensional dots and boxes to play with your one remaining maths friend at that stage. That would be great. So let's see if we can investigate the early case. In the one-dimensional hypercube, I think we can agree that one edge is acaudal because there's no other options really. So the first proper term in the sequence is 1. But on the square, what's the longest acaudal path, Jocelyn, that you reckon you could draw here?
I feel like if you do 2, then you can always draw a third to join them. Oh, but you have to use one of the ones that exists. You can't just draw a random chord. Okay, yeah, then 2.
So you're saying you can't now draw a third one because then you'd have made a chord. Yeah, you're absolutely right. So the longest achordal path on a two-dimensional hypercube is 2. Hope you get the fun one. What's going on with a three-dimensional hypercube?
Okay, so the same thing will happen is that on the top face, we can have 2. So then I can't go across. So my only option is to go down. And then I can't go along the back. So I have to go here. I can't go up because that would be a chord. And I also can't go across. So I think I'm done, right?
So let's check, because I think you might be right. 4 is indeed the longest path that you can make on a three-dimensional hypercube. So I've still got quite a few boxes left to reveal. Who is feeling dangerous enough to try a 4-dimensional hypercube? Now, this is one that appears in pop culture a lot because it's the kind of thing that people think is science fiction, but it is in fact mathematical facts. So how do we draw the hypercube in 2 dimensions? That's a great problem to ask. Over to you guys. What is the longest open achordal path in a 4-dimensional hypercube that you reckon you could draw?
So my initial thought was 9 because, okay, so we have 4 from the first cube and then we connect to the bigger cube and then we can do 4 again. It's maybe slightly more than 9 if you can kind of go back from the big cube to the little one again without adding more chords.
You might remember that I told you the non-achordal version of the problem is one that it's impossible to fail, in that if you follow the rules, you just will find the longest one. Do you suspect that this is impossible to fail, or do you suspect that this might be surprisingly difficult to complete?
I can imagine it'll take a few goes to kind of figure out where you start from, maybe.
So you said, well, it shouldn't matter where you start from because it's a lovely symmetry group.
True.
Let's see if we can hit 9 with your strategy. And I think you said we'll do the same thing that we did on the first cube, which I think was these 4 here. And then I'm going to change to a slightly thinner pen. Where would you like to go from here?
So if we then move like into the smaller cube.
We kind of have to, don't we? Because we can't go to anywhere else. So that's no decision. But now I think you do have 2 choices to make. I think you can go up,
So
up or left.
So yes, and we want to make the choice in a way that we can still try and do 4 on this cube. So
should we block off the ones you can't go to? Would that be useful?
Yes, that would be good.
So I think that's an easy task. We can't get that one, or that one, or that one, or that one. Is that it? I think so.
Okay, so then we can do this and we can do this.
You can, yeah. And at that point, you're stuck because you definitely can't get down there. Yeah, we couldn't have done this one. Fantastic. So what's that? 1, 2, 3, 4, 5, 6, 7?
Yes, or if we went the other way, if we went up and then
that one's off limits.
Yeah, so we could only have gone up, so just going up would have been worse. Okay.
But it is interesting to note that you have now found a choice where one path leads you to a failure. So it's not impossible to fail. It is definitely very possible to fail at this problem, which we like. But you are correct. So 7 is the correct answer for a 4-dimensional hypercube. It is 7, and I'm gonna speed you through the next one. So that was 4. In 5 dimensions, we get 13, surprisingly small. In 6 dimensions is 26. In 7 dimensions is 50. Do you want to know what it is in 8 dimensions?
99.
Oh, that is a lovely guess, regular listeners to the show, especially for this segment, will know that I love questions that are either it's surprisingly small, absolutely massive, or nobody knows. And question 8 dimensions, used to fall into the category of nobody knows, but very recently someone has proven it's 98, off by 1. That is incredibly pleasing, isn't it? It was strongly conjectured for a long time that it was 97. Someone found one that was 98. I can't remember their names, so I'm not going to be able to credit them, but that is a recent development. And that's where it stops. So we don't know what happens afterwards. Now, there's no limit to the number of dimensions. You could definitely have a 9-dimensional hypercube. We just have no idea what the longest open acordial n-dimensional hypercube is. People are still hunting for this. And I use the phrase hunting because the research papers say hunting for thee. And I realize now that I haven't actually given this a name yet. Do you want to know the name of the sequence? And this is the XKCD post. This is the snake in a box sequence. And it is because we try to trap a snake inside of a box to see how long that snake can possibly go. So people are still hunting for the longest snake in a box, which I think is really quite fun. And they're also doing it using evolutionary techniques, which I think is also a very fun word to use in this context. Do you want to see some open research for what's coming up? So these are the current known records. I should point out that we don't know that they are the longest possible snakes in a box, only the ones that we have found. And we are confident up to 8. Beyond that, it is still undetermined. So if anyone wants to go out and research this, you can very easily draw a 16-dimensional hypercube and go and start drawing snakes inside of it. Last things to do then today is to do some plugs. Jocelyn, what do you want to tell us about?
I thought I would talk about my company called Poindexter Labs. We provide data sets, which, well, for a lot of audiences, that wouldn't be a great way to start a plug, but for yours, I think actually that might draw them in. So basically, we write maths problems that are interesting and that stump state-of-the-art models, and anybody that can successfully stump a model with a maths problem is welcome to join the team and get paid for it. They just send me an email, find me on LinkedIn. I'm sure there'll be a link to me in the show notes.
Fantastic. Thank you very much. Yeah, we'll put those links in the descriptions. If you want a job, then you've heard it here first. You can go and get a job as a maths creator. Lovely. And Hope, what would you like to plug today?
Well, I'm a fairly new maths YouTuber myself. I'm currently a PhD student in maths, and I think a big part of that was I was kind of raised watching a whole bunch of maths YouTube. So essentially what my channel does is, if you are similar to me and you love watching mathsy things on YouTube, which if you're watching this video, you probably do, and you want kind of a little look behind the scenes at someone who is trying to do maths communication in various different styles that you might see across YouTube, and talk about what it's like and why I think these styles of communication work, then my channel is for you. I'm, as we record this, still working on my first video, but if all goes well, when this podcast is live, my first video will be also. So if you can link to my channel, that would be great.
Fantastic. Links below as well. You can go and check that out. Please go and give Hope some support. For myself, I'd like to plug this very project. We are on episode number 5 now in what I'm calling the soft launch phase of the project, where we are just finding our feet, getting the tech working and seeing out what kind of format we want to do. Coming up at the end of August, though, we have the Talking Maths in Public conference, which might be able to see many of you at. And that is where we're going to do the hard launch, where we can say, hey, this is what we're doing, come join in. And you too can come and join in, be on the show, be a guest, come tell us something fun about maths. You really have absolutely no barrier for entry, any level, any quality, any set of confidence. We're trying to make it as easy access as possible. So give me a shout if you want to be involved, and you'll be more than welcome to, and I'll have a chat with you for a few hours of an evening. Also, if you like maths history, I do a little maths history podcast. And you can go and support that as well if you like. Fantastic. So last is just goodbyes. So that's all for today, and that is a goodbye from me.
Bye from me.
Bye from me.